Okay, so in this lecture, let us discuss the implementation of FIR filters in parallel form. Now, it is possible to do a parallel implementation of FIR filter. Okay, generally, when I say parallel, this parallel is usually resorted to when you wish to speed up the process, like you have parallel algorithm, right, and parallel software, right? So this parallel algorithm, parallel software is faster than a serial processing. Okay, so generally this parallel processing or parallel is resorted to speed up the process. Therefore, it does the job in a much faster way than a serial processing. Okay, so parallel processing is much faster than serial, but in the FIR case, that does not happen. This parallel processing or parallel structure will not help us to improve the speed. You know the reason why? Because if you have h of z, which is summation hk z to the minus k equal to 0 to, let's say, 7, then 7 delays are needed whatever you decompose, right? So in this, however you decompose it, it needs 7 delays. But in general, parallel means what? You write the summation as follows: summation of hi of z. So there will be at least one hi of z which will contain 7 delays, right? Therefore, the processing time cannot be reduced by parallel implementation in FIR case. So in FIR case, parallel implementation will not reduce the processing time, will not help us in any way. But this is not true in IIR. IIR, it is good. Okay, reduces the processing time. But in FIR case, it will not help us in any way. However, still, even though it is not helping us to decrease the processing time, we are going to discuss. The reason is parallel implementation is useful in the context of multi-rate signal processing. Multi-rate signal processing. Okay, when I say multi-rate processing, that means interpolation and decimation. So whenever you are discussing multi-rate signal processing, then this parallel decomposition helps there. Okay, so when I rate multi-rate, that means what I mean is interpolation, INTER, decimation, and the decomposition in this interpolation and decimation is done in a particular manner, and that is called polyphase decomposition. So we will briefly touch upon this topic because it has become now an integral part of any programmable digital signal processor, right? This interpolation and decimation becomes a very important part in digital signal processing. Okay, so this interpolation and are resorted for various reasons, but the main reason is that it reduces the hardware complexity of the structure. Reduces hardware complexity. And we will illustrate this with reference to a particular transfer function, let's say of order 8. So h of z is equal to h0 plus h1 z inverse plus h2 z to the minus 2 plus etc. plus h8 z to the minus 8. Now we can decompose this transfer function in various ways. Let us take the alternate terms. So let me take h0 and then h2 z to the minus 2 plus h4 z to the minus 4 plus another next alternate term is h6 z to the minus 6, and the next alternate term is h8 z to the minus 8, right? Plus then take remaining terms h1 z inverse plus h3 z to the minus 3 plus h5 z to the minus 5 plus h7 z to the minus 7. Okay, so we have taken the alternate terms. And if you look at this guy contains only even subscripted coefficients. Even subscripted coefficients. And this one contains odd subscripted coefficients. And obviously I can write this even subscripted coefficients as follows. I can write E0 of z squared, because the power of z here, if you look at here, power of z is 2, 4, 6, 8. So I have written this 2 here. So they are power of z squared. And then this part becomes, I can write as, I can take z inverse if commonly outside in this, then you will be having h1 z to the power 0 plus h3 z to the minus 2 plus h5 z to the minus 4 plus h7 z to the minus 6. Once again, if you notice here, they are even powered coefficients. So this E0 of z squared plus z inverse, let me call this guy as E1 of z squared. And obviously the implementation would be that I have two paths, one for E0 of z squared, and the other is z inverse times E1 of z squared. Okay, so this is h of z. H of z, I can write y of z divided by x of z. So x of z, this is, you can, one more step, let me write on here. You can write this as y of z equal to E0 of z squared times x of z plus z inverse E1 of z squared times x of z. So x of z, this x of z, I can first multiply by this guy E0 of z squared, and then there is a delay, you put a delay here, z inverse, and then you put E1 of z squared, and then these two guys are added, and this is your y of z. Two parallel paths, but as I said, they do not increase the speed. They do not help in making the processor faster. Okay. However, you know that if I have a factor of 2 interpolation, then the z transform, it is squared, right? You look at here, z transform is squared, and therefore if I decimate this by a factor of 2, I can realize E0 of z and E1 of z. So the speed thereby increases. So this is one of the tools for interpolation and decimation for multi-rate signal processing. And there is nothing sacred about breaking up into two transfer functions, right? So here we have broken up into two transfer functions, even powered subscript coefficients and odd powered subscript coefficients. I can also make a three-phase decomposition, right? It's not like that you can make only two coefficients, two set of coefficients. I can make in terms of three-phase decomposition as h of z is equal to E0 of z cubed plus z inverse times E1 of z cubed plus z to the minus 2 E2 of z cubed, and this E0 of z cubed now will be h0 plus h1 z to the minus 3 plus h3 z to the minus 6. That's it. And E1 of z cubed will be h1, am I writing correctly? I'm sorry, this is h3. Okay, h1, okay, yeah, h1 plus h4 z to the minus 3 plus h7 z to the minus 6. And this one, I'm sorry, this one E2 of z to the cubed is going to be h2 plus h5 z to the minus 3 plus h8 z to the minus 6. See, here also I have z to the minus 6, here also z to the minus 6, and here also z to the minus 6. And the realization is obvious. You have three paths, right? One path is E0 of z cubed, and the next one is you delay by one element, right? And you put E1 of z cubed, and then you put one more delay, and then you put E2 of z cubed. You put an adder here. In order to respect the hardware realization, I should not give more than 2 input to an adder. So I have given only 2 inputs. You put one more adder here, and then this is my output y of z, and this is input x of z. Therefore, I have 3 paths, and you recover 2 extra delays. Okay, this one and this one. But again, if you count, the total number of delays that you are using is still 8. Okay, so that's it. And if you take this one is multiplied by z to the minus 2, right? So here in this point z to the minus 2, and here if you look at, it has h2 plus h5 z to the minus 3 plus h8 z to the minus 6. Now this z to the minus 3 and this z to the minus 6, if you multiply, again you need z to the minus 8. So I need 8 delays. So you are not reducing the number of delays. So if the delays are the same, that means you are not increasing the speed. This is no way helping us to improve the speed. Okay, if you take this path, again you need 8 delays. 8 delay means, the speed is not increased. So you can also appreciate that the total number of delays required in the implementation of polyphase decomposition is much greater. Okay, why? It is much greater than in direct realization or cascade realization. However, the number of delays can still be kept at 8 for this structure by sharing the delays. Okay, you can share the delays from this guy, share the delays from this guy, like that. If you share the delays from different parallel paths, then you can reduce the number of delays. So we wrote h of z is equal to e naught of z cubed plus z inverse of e1 z cubed plus z to the minus 2 e2 of z cubed. And what is this? This is the three-phase decomposition, right? Three-phase decomposition. Okay, do not confuse with the three-phase power. It will illustrate this with reference to this particular example. Okay, 8th order example. The trick to obtain a realization in which no more than 8 delays are used is to share the delays. Let's say this guy needs 3 delays, right? And 3 delays here, and here also 3 delays. So if I draw the block like this, z to the minus 3, and here z to the minus 3, it is a 3 block cascaded to each other. Okay, this block indicates I have z to the z inverse, z inverse, z inverse, and from here also 3 delays are cascaded like this. Okay, so let's say this is point 1, point 2 and point 3. From point 1, 2, 3, I first combine signals to obtain E0 of z cubed. And then from point 1, 2, 3, I can combine the signals to obtain E1 of z cubed. And then similarly point 1, 2, 3, I can combine to obtain E2 of z cubed, but in between I need 2 delays. So that's a trick that one generally uses to reduce the number of multipliers. For example, for E0, I will have to take H0. Let me take point 1, and this is given to z to the minus 3 and z to the minus 3, and in this point H0, and from here H3, both are added, and then H6 is delayed by 6 units. This is E0 of z cubed. Next I construct E1, isn't it? For E1 I shall have multiply by H1. So let me use a different color. H1, and then this point, this is H4 multiplied by z cubed minus z cubed, both you add here, and here this one is H7, and this is E1 of z cubed. Is that correct? Okay, fine. This is E1 of z cubed. And then if you look at E3, then let me redraw the diagram again. I need some space. Okay, so in this case, this one is H2, and here H5. The figure is becoming a little bit complicated, and you put an adder here, and then your H8 is again multiplied by z to the minus 6, so you put adder here, and this is E2 of z cubed. Okay, and this u2 of z cubed is multiplied by 2 delays. So you put one delay here and then put an adder. So let me use okay, then you put one more delay, and this is it becomes complicated. Let me write down here. Put adder here. This is your final y of z, and this point is e naught of z cubed. Now what is e2 of z cubed? This is h2 plus h5 z to the minus 3 plus h8 z to the minus 6. That's what we did here. See, h8 multiplied by z to the minus 6, h5 multiplied by z to the minus 3, and h0 no multiplication, right? And then if you look at this point, this is e1 of z cubed. This is h1 plus h4 z to the minus 3 plus h7 z to the minus 6. So exactly this red line realizes this expression. And e naught of z cubed is h0 plus h3 z to the minus 3 plus h6 z to the minus 6. But if you look at the expression, in this expression here, this e2 of z cubed is multiplied by z to the minus 2. e1 of z cubed is multiplied by z inverse. So that is why this z inverse is coming, and this 2 z inverse is coming because of this guy is multiplied by z to the minus 2. That's it. So e2 of z cubed goes through 2 delays. So first delay is, I put it here, e1 of z cubed goes through 1 delay. So I combine e2 of z cubed and e1 of z cubed and then use another delay, this delay. Therefore I made sure that e1 of z cubed is multiplied by this delay z inverse, and e2 of z cubed, this one, is multiplied by this delay and this delay to give the output, which is h of z. So this is a trick that one can imply to make the structures still canonic. Why is it canonic? If you count number of delays, here 3 delays and here 3 delays, 3 plus 3 6, and this one is 7 plus 1 7, and if you add here 8. So we used only 8 delays, therefore this is canonic in structure. Okay. So in general, if your transfer function h of z is equal to h0 plus h1 z to the z inverse plus dot 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 plus h suffix capital M minus 1 z to the capital M minus 1. I mean, I'll go back and forth between the order and the length, so that we should be careful. The length here is M, but what about the order? Order is M minus 1. And you can make an L phase decomposition. Okay, so your transfer function in this case h of z is equal to summation of z to the minus m e suffix m of z to the L. See, if you look at here the subscript is 1 and the power is minus 1. Here the subscript is 2 and the power is minus 2. and here the subscript is 0, therefore z to the 0, like that I can write, right? So here also if the subscript is m, then z to the minus m, and this power is constant because we are talking about L phase decomposition. And then what about the limit? The limit goes from m equal to 0 and m capital M by L, and this m by L may not be an integer, therefore I can take the floor function. There is no guarantee that m will be divisible by capital L. It will be integer part. Integer part is usually denoted like this. So m by L, and this symbol denotes integer part of capital M by capital L. For a three-phase decomposition, we had E0 of z cubed. For L phase decomposition, we have E0 of z to the L. And h of n will be obviously 0 for n greater than or equal to capital M. Some of them may not have the same number of components as others, because h of n is equal to 0 for small n greater than or equal to m. I mean, I don't have any other term. Okay, so this is the general L phase decomposition of length m FIR filter. Okay, this I think you are clear about this, because we had z to the 0 E0 of z cubed plus z inverse E1 of z cubed, isn't it, plus z squared E2 of z cubed. Now look at the subscript and this power. I'm sorry, this is minus 2 actually, I think, z to the minus 2. So z to the minus 2 E suffix 2 of z cubed, and this 3 indicates three-phase decomposition, and this subscript and this power should be the same. That is why I put this suffix as m and power also m, but there should be a minus. Okay, that you should be very careful. So that's all about parallel implementation of FIR filter. So in the next lecture we will discuss linear phase FIR filter. This is very important topic. We will discuss in the next lecture. So thank you very much.